Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. I am Sylvia Neseroy. In this opportunity, I would like to present to you about my review on a paper that I will use as a reference on my final project. First of all, I will explain to you about the paper that I used. The first one is a dual band slotted waveguide antenna arrays for radar applications, and the second one is a terahertz slot antenna optimization using analytical technique. This paper described the design and fabrication of a dual-band slotted waveguide antenna array for radar applications. The surveillance radar system must provide two principal pieces of information: their distance and identification of the target. Also, the surveillance system needs to be multi or dual-band in order to acquire a greater amount of information on a particular region. So, the purposed antenna provides two operational bandwidth while maintaining high gain. The structure radiates over two different frequencies bands at the same time, enables to send different targets with the same device, reducing cost and size. So the slide is showing the concept of the antenna. The first figure shows side views of the slots designed for S-band. The signal will pass through the slots and propagates. The remaining energy will reflect in the end of the waveguide and will be constructively propagated with the earlier wave portion. The same behavior will happen for the C-band that's shown in the second figure, where x is the distance between the last slot center and the waveguide end, s is the slot size, z is the distance between the slot and the center of the antenna, and fp is the distance between the probe and the beginning the slot of waveguide antenna array structure. And the last figure showing the feeding structure view. This section presents the fabricated antenna prototype. The proposed antenna has two widest bandwidth. It's from 2.1 to 2.3 GHz with a maximum gain 14.461 dBi, and the second bandwidth centered at 4.91 GHz with a maximum gain 17.64 dBi. The antenna has 11 slots for S-band and 22 slots for C-band. To expect the gain for the higher frequency band is expected to be at least 3 dB higher than the low. So the conclusions are: a novel concept of a dual-band slotted waveguide antenna array for radar applications has been successfully proposed, numerically analyzed, constructed, and experimentally characterized. The antenna structure is based on two groups of radiating slots in order to provide at least two frequency bandwidth. The first one from 2.1 to 2.3 GHz and the second one from 4.88 to 4.94 GHz. The novel structure enables diverse sorts of tracking using a unique structure by taking advantage of different radiation patterns from two frequency bands. So this is the second paper that I used with the title A Terahertz Slot Antenna Optimization Using Analytical Techniques. This paper shows how analytical techniques can be used for optimization of terahertz slot antennas. Slot antennas are very popular microwave antennas, and slotted waveguides are used for high-frequency radar systems. The position of the slots affects the intensity of the transmitted power by being a direct cause to the impedance matching of the antenna. Good impedance matching will cause maximum efficiency of the power transmission. We can summarize the design procedure for waveguide slot antenna as follows. First, choose the number of slots required for the desired gain and bandwidth. Second, choose a waveguide size appropriated for the operating frequency. Third, calculate the wavelength in the waveguide at the operating frequency. Fourth, determine the slot dimensions, length, and width appropriated for the operating frequency. Fifth, determine the slot position from center line for normalized. Sixth, space a quarter lambda or 3/4 lambda between the center of the last slot and the end of the waveguide. But there's a small difference between the analytical and simulation results. The difference is due to the simplified assumptions that were taken in the analytical design. Despite the difference, good approximation of antenna's performance, antenna spectrum, bandwidth, and gain can be made. So this is the conclusion of this paper. It's recommended to use an analytical model to optimize the design and obtain the required antenna spectrum and performance. Using the analytical design information, one can perform a simulation. Then, according to the simulation results, modify the parameters until the optimal results are obtained. From this paper, I can conclude that these papers are suitable as a reference for my final project later. Thanks for your attention. Wassalamualaikum warahmatullahi wabarakatuh.